Moving ahead in our Doppler lecture, we'll discuss continuous wave and pulse wave Doppler. So the fact that we can tell the difference between positive and negative flow all comes up because of bidirectional Doppler, and this is the common configuration now of our clinical systems. That bidirectional Doppler tells us that yes, flow is going towards the transducer or that it's going away from the transducer, telling us those positive and negative Doppler shifts. There's a couple different ways to display or to get across the bidirectional part of the Doppler. One way is to use audio, in which two speakers are used. One is going to put that audio information out for positive shifts, and then the other one is going to put audio information out for negative shifts, so you can use your ears to kind of hear the difference in how blood is moving in relation to the transducer. More often though, we are going to be using a graphic display of bidirectional Doppler. And that is when we put our continuous wave or our pulse wave onto our duplex, let it run, and we get that spectral tracing down on the bottom of our image. So positive flow then is usually displayed above the baseline or on the side that has the plus sign. And the negative flow is going to be displayed below the baseline on the side with the negative sign on it. And all of this occurs because of a tool that the machine uses called phase quadrature. It's also known as quadrature detection. So memorize this term. It is a vocabulary term that goes along with bidirectional Doppler, and what it does is it reduces all the extra information coming back from the Doppler shift and kind of figures out what side of zero it's on so it can be displayed appropriately. So there's much more physics behind the phase quadrature. Just recognize that phase quadrature is the reason for bidirectional Doppler displays. So the first type of Doppler that we're going to discuss is continuous wave Doppler. For the purposes of general and echo both listening to this lecture, I will put out there that general ultrasound does not typically use continuous wave Doppler, but you are still required to know it. Where echo tends to use this a little bit more, they deal with much higher frequencies, and we'll learn why they might want to switch to a continuous wave Doppler. So continuous wave Dopplers require two crystals, and that's it. It's going to be one to transmit sound and one to receive. When we think about our transducers that we use typically, they are pulse waves, so the same crystals send out sound, turn off while they're receiving that sound, and then go back and forth between their transmit and receive capabilities. Continuous wave Dopplers, one is just constantly pumping sound out, the other crystal is just constantly receiving that sound coming back. The big advantage to continuous wave Doppler is that it can very accurately measure super high velocities. Pulse wave, as we'll learn later, has a limit to what it can measure. Continuous wave does not have that problem. It can really get those high velocities and is very accurate at it. The disadvantages to continuous wave Doppler, though, is that we don't really know the exact location of the sample. That's because continuous wave Doppler does not produce anatomical images. So we can guess as to where our continuous wave sample is being taken, but we cannot perfectly place it exactly where we want to. So information is going to be displayed from where the transmit beam and the receive beam are also overlapping. So this limitation falls into the range ambiguity piece of it. And we'll discuss that a little bit more in a different slide with some pictures. The other disadvantage to continuous wave Doppler is that we can't TGC or change the gain that is coming back on those received echoes. So the problem with that is that deeper reflections might be incorrectly displayed as a low amplitude, so it would be like a really light gray in our spectral tracing. One is actually a strong reflector, it's just deep into the tissue, or deep reflections might be incorrectly displayed as just a few blood cells. So in that last slide I had mentioned that we can't really tell for sure where the continuous wave Doppler is coming back from, and what it actually comes back from, we have the transmitting beam going into the body, and as it hits things, it's going to bounce back and hit the receive crystal. The only spot that we're going to get information from then is anywhere along the line that the transmit beam and the receive beam overlap one another. As these are displayed on our spectral tracing then, we're going to get varying velocities as things overlap in that area. The problem with that then is that we get some range ambiguity. We don't know if these reflectors are coming from high up or are these reflectors coming from lower down into the body. So that's the range ambiguity part of it. We also can't say for sure are they strong reflectors versus deep reflectors because we can't TGC through our continuous wave. So if we're getting some light reflectors in here, it's hard to say is it just a deep tissue problem or is it truly a low amplitude reflector. So continuous wave has a little bit of issues with that. The best part of it though is that there's no aliasing. We love continuous wave because there's no aliasing with it. So with continuous wave Doppler, we need to understand how the continuous wave transducers work with it. So there are a couple of different types of transducers that can do continuous wave. And the first one is a dedicated continuous wave transducer. These are really simple transducers. They have two elements. Each are going to be a semicircle shape. So you'll look like something like this. They usually have round faces. Again, one is going to be for transmit and the other one is going to be for receiving. These do not create an anatomical picture, because again we need pulse waves for anatomical pictures, and they don't have any backing material. And because they lack that backing material, we're going to get a very narrow bandwidth, which will give us that high quality factor and higher sensitivity. It's these three things that make it really good at very high velocities. The other option for continuous wave transducers is to use a dual use transducer, and these are going to be our array probes. So it's going to use a set of elements to send and receive, so it only needs, this is our array, it only needs a couple elements to do that continuous wave portion of it, and then it's going to use the rest of the elements to do our duplex imaging where we get our actual picture and then our continuous wave underneath it. So it'll simultaneously perform anatomical imaging and continuous wave transducers. For the echo folks, our dedicated continuous wave transducers are going to be our PDOF probes, and then our dual use transducers will be our typical cardiac probe. For general sonographers and vascular sonographers, when we use the Parks machine, those are actually continuous wave transducers, and you can actually see the crystals right on top of those probes. So opposite of continuous wave, then we have our pulse wave Doppler, and these should be a little bit more familiar to you guys, as these are what we are using day in and day out. Whenever we are doing our duplex, where we have our picture up on top and then some sort of spectral tracing on the bottom, that is most likely using our pulse wave Doppler. So with pulse wave Doppler, we really only need one PZT crystal, as it's going to alternate between transmit and receiving. The advantages of the pulse wave Doppler is that we can then select exactly where we want to get information back from. You may have noticed when you activate your pulse wave Doppler, you get this beam line with the two little lines running parallel to one another, which is called our gate. We can place this gate exactly where we want it to be, and so we know exactly where we're getting information back from. When we do this, we are fixing that range ambiguity, and we call that range resolution, range specificity, or freedom from range ambiguity artifact. So we can pick our exact location that we want to get information back from. That's a great advantage for it. It's also advantageous because we, as sonographers, can position that sample volume or gate anywhere we want. So if I've got a huge blood vessel and I want to sample down here, or up here, or over here, I get to choose, because that is the benefit of using pulse wave Doppler. The disadvantages of pulse wave Doppler, though, is that it is very inaccurate at measuring high velocity signals. There is only so much that the pulse wave Doppler can handle, and when it reaches its limit, we're going to result in that aliasing, where we kind of get that wraparound or inappropriate display of color or spectral tracing on our graphs. So again, pulse wave Doppler, really awesome because we can say I want to sample right here, drop my gate in, and that's exactly where I'm going to get information from. I don't have to guess, am I getting it from somewhere up here, am I getting it down here, as we did with the continuous wave. I get to pick the exact spot. The drawback of pulse wave Doppler though is that aliasing. That is a very big drawback and we need to correct for it. So just like continuous wave Doppler transducers, we do need to know about pulse wave Doppler transducers. And that's pretty much all the transducers that we're using for anatomical imaging. They are all going to have the dual use ability to do duplex imaging. Duplex imaging again is when we have our picture up on top with our pulse wave spectral tracing down on the bottom. In this event, the transducer uses one crystal for that pulse wave information, and it's going to use the rest of the crystals to create our anatomical picture. With pulse wave Doppler transducers, they are going to have low quality factor, a low sensitivity, and wide bandwidth pulses. These three factors are what result in the aliasing and the decreased sensitivity to higher frequencies. So here's an example of a continuous wave versus a pulsed wave Doppler. We're looking at the same area in the heart. Most likely the sonographer started with a transducer that had the pulse wave, and so we're looking at this one here. And we can see that we have our baseline running through the middle here. We have information that's coming down and then wrapping back around. In this example, there's quite a bit of aliasing in the mitral valve regurgitation. To fix this, to get a clear idea of what's going on, the sonographer switches to a continuous wave, because remember, continuous wave can handle super high velocities. Continuous wave, you'll see we are getting true values of that high velocity. We're not getting that wraparound aliasing. So again, pulse wave, great for picking the exact location that you want to get information back from, but it's going to result in aliasing if there's very high velocities. At that point, you would switch to a continuous wave transducer to continue interrogating to get accurate high velocities. So we've talked about aliasing a couple times now, one in the artifact lecture, as it is technically an artifact, and again a little bit in this lecture as we've discussed the difference between continuous wave and pulse wave and why we would want to switch between the two. So aliasing is important to understand, as we do need to be able to correct for it as we are interrogating velocity of blood. So aliasing is the false identity in that the incorrect display of very high velocities below the baseline. So as we have our baseline here and we reach our Nyquist limit at the top here, anything above our Nyquist limit is going to be redisplayed below the baseline. This is a false identity. Technically, this would be a negative number, even though it really should just be up on top of where we were. This happens only with pulse wave Dopplers. It does not happen with continuous wave Doppler. And it happens because the Doppler sampling rate is too low. So that Nyquist limit we kind of consider to be a speed limit. And that aliasing is going to appear when the Doppler shift exceeds the Nyquist limit. This equation here you will need to memorize. The Nyquist limit is measured in hertz, and it equals the PRF divided by 2. PRF, as we've learned before, is another word for scale. So memorize this. If the Doppler shift exceeds the PRF divided by 2, we're going to get aliasing. So remember that aliasing is because the Doppler shift is exceeding our Nyquist limit, and that the Nyquist limit is the PRF divided by 2, or in other terms, half PRF. This is another example. We have our baseline here. Our velocities are reaching the top of our scale, or our PRF, and because that's our Nyquist limit, they are wrapping back around and being displayed below the baseline. So as a sonographer, you're going to need to know how we avoid aliasing. The first option is to increase the Nyquist limit. we increase the Nyquist limit by increasing our scale or decreasing the depth at which we are imaging at. When we decrease our depth, we are going to have a higher PRF. If we have a higher PRF, that means we can have a higher Nyquist limit. When we image deep into the body, that is going to cause a low PRF, which causes a low Nyquist limit, causing more aliasing to occur. The other option is to reduce the Doppler shift. So we can do that either by lowering our transducer frequency. So with a lower transducer frequency, we're going to have low Doppler shifts, which means that they are less likely to exceed that Nyquist limit. And as you remember back from last lecture, that those frequencies are directly related. As we switch to a 5 megahertz transducer from a 2.5 megahertz transducer, our Doppler shift went from 4,000 to 8,000. As that Doppler shift increases, it's more likely going to exceed that Nyquist limit. So making sure to have an appropriately low frequency will help with aliasing. So this slide kind of goes over the 5 things that we can do as sonographers to correct for aliasing. Remember all of them. And it also kind of goes over why it might not be the best idea for the correction. But to begin with, when we see that aliasing occurring, we can adjust the scale to the maximum. The machine pulses at less than maximum allowable rate. And then when we increase the PRF, we can increase that Nyquist limit. So when you have your spectral tracing on the bottom and we have our numbers over here, we can increase our PRF or increase our scale, and we consider this our scale, and that'll help to increase our Nyquist limit. The problem with it though is that it doesn't always compensate for extremely high velocities. At some point we're going to max our machine out, and if our velocities are even higher than that, then we're kind of out of luck with increasing that Nyquist limit. The next option is to select a new window that allows for shallower sampling. So as we heard about on the last slide, when we image more shallow, we can increase our PRF, therefore increase our Nyquist limit. With that though, you're going to need to reset your sample gate and figure out how to insonate the area that you're interested in because you've now changed your window or pushed a little bit harder. The third option for correcting aliasing is going to be to select a lower frequency transducer. Oftentimes we are imaging blood vessels with about a 9 megahertz transducer. Say we're getting lots of aliasing in here that we cannot correct for, then we could switch down to maybe a 2.5 megahertz transducer. That's going to create lower Doppler shifts, which will most likely not exceed the Nyquist limit. The problem with this though is that we're going to get lower quality anatomical images because our resolution is not as high with the low frequency. The fourth option for correcting aliasing is to shift the baseline. Normally when we come up, our baseline rides right in the middle with even numbers on either side of it. We can actually shift that baseline down, which will give us more room above or below the baseline to help display more of the waveform. This doesn't change the Doppler shift at all, it just changes how it's displayed on our machine. This is going to be ineffective, however, if that signal wraps all the way around itself. We just won't be able to separate out enough room to display the whole waveform. Our last option then is to switch to continuous wave Doppler. There's never going to be any aliasing with it. The only problem is that we include that range ambiguity and that we can't pick our spot that we want to sample from. So memorize these 5 ways of correcting aliasing. So if it helps, we'll cover those 5 ways again, and we can think of it in a different way, as if the Nyquist limit was the speed limit, and you're about to get a ticket, which would be our aliasing. So how do we get out of our speeding ticket? So the biggest two things that we're going to look at to avoid getting our speed limit or our speed ticket is that we're either going to raise the speed limit or reduce our speed. So say we want to raise the speed limit, which we're calling our Nyquist limit. We do that by increasing our PRF frequency or increasing our scale, or we do it by decreasing the depth. These are the two ways that we're going to be able to raise that speed limit. The other option is going to be reduce the Doppler shift or reduce our speed, and we do that by reducing our transducer frequency. These three options are going to be the most reliable way to avoid aliasing while still using your pulse wave Doppler transducer. Your other options then in the clinical setting are to change your baseline or switch to continuous wave. This picture exemplifies even further what the aliasing, how it relates to the Nyquist limit. If this is our spectral tracing and we have our Nyquist limit set here, anything above that is going to go past the top of our scale and be wrapped around and put on the bottom. So the options are to reduce the Doppler shift, and we do that by reducing the frequency of the transducer, or we raise the Nyquist limit, and we do that by increasing our PRF or getting closer to the area of interest by reducing our depth, both of which will increase the PRF. So again, correcting that aliasing, it's going to be really important as a sonographer that you really understand these concepts, why we're changing scale or PRF, why we're going to try to get closer to the area that we're interested in, because decreasing our depth increases our PRF, how switching transducers is going to change the Doppler shift, why a baseline shift might work, and why we would switch to continuous wave Doppler. As you guys take your boards, you're going to be having these questions on there that are going to have a console with all of this information, all these dials and stuff that you can change, and it's going to give you a picture of a blood vessel or something that's going on with aliasing, and it's going to say, hey, what can you do with this? You need to be able to look at all the settings that that fake console is set at and see what you can change to help get rid of that, all of that aliasing. So, if your PRF is maxed out and you're as shallow as you can get, you don't have a continuous wave option, and your Doppler waveform is wrapping all around itself, the only thing left that you can do is change your transducer. So you really need to be able to kind of look at those problems in multiple ways and see if you can kind of check off down this list how you're going to correct that aliasing. So another thing with our spectral tracing is that we have lots of gray shades that end up on that spectrum of our spectral tracing. What ends up coming back on the tracing is the amplitude of the reflected signal and the number of blood cells creating a reflection. So as we get our reflections, the higher up it is a higher amplitude, and the width of the line kind of shows us the number of blood cells that are creating that bit of reflection. So we consider the spectral Doppler gain to be an important part of setting the machine appropriately. If we increase that gain, we're going to cause more background noise to appear behind the waveform. We're going to get that snow behind our true waveform. And what this can do is actually overestimate the velocity measurement. The opposite of that, then, we can actually decrease our gain way too much, which will cause our waveform to be too light, which will cause the waveform to either vanish or really underestimate the velocity measurements. My rule of thumb is to churn my pulse wave gain up until I just start to get little speckles behind it, and then I back off one, and that should give me an appropriately set anechoic background to my white spectral tracing. So we can see in this first example here, we have maybe a little too light of a spectral Doppler gain happening here to more of our appropriate spectral Doppler gain, and then getting into our very, very high set spectral Doppler gain. You can see all this little junk that's kind of hiding behind that waveform. But the sonographer went through and measured at different points. Same blood flow velocity through all of it. But what we're finding is that in the lighter area, the velocity was measured at 91.5 centimeters per second. In the very bright area, it was measured at 109 centimeters per second, and in the appropriately set area, we were getting 104 centimeters per second. So you can see how if it's set too low or set too high, it's going to change what our velocity measurements are coming back at. Another example in picture B here, we have an appropriately set section of Doppler gain here. We have a nice black background, nice white spectral tracing, and our measurement came up at 86.4 centimeters per second. As the sonographer cranked up the Doppler gain, we started getting all this little snow, these white marks behind, measured again, and they get 101 centimeters per second. And that's a pretty big jump, and that might be enough to put somebody in between two categories of grading stenosis, or plaque measurements, or regurgitation. It might just be enough to tip them into another category. So we have to be really careful that we're setting these appropriately. Some other hints on optimizing pulse wave Doppler. Again, we want that spectral Doppler gain to be set appropriately. If we put too much noise in that background, we're going to cause that overestimation of velocity measurement. If it's too light, then we're going to underestimate our velocity measurement. So again, set that appropriately so we're getting good measurements through there. And also make sure that your wall filter is set appropriately. What the wall filter does is says, hey, we don't want anything displayed over 5 megahertz, over 50 megahertz, and so on, or hertz, excuse me. And if we set that inappropriately, we might lose some information. If we set it appropriately, we might clean up our pulse wave Doppler tracings a little bit more. But in the end, the wall filter really shouldn't affect the appearance of your higher velocity flows. It really only deals with those low level velocities that are going to hang out near the baseline. So the wall filter will kind of help to clean that up a little bit. So this picture kind of exemplifies that. In our first example, we have this little wall thump, some extra little noise that's happening through this area, and the wall filter is set at 50 hertz. So it's saying we don't want anything to be displayed that rides under 50 hertz Doppler shift. If we turn that up a little bit to 75 hertz, we get rid of that wall thump. So it just really cleans up our spectral tracing quite a bit more, makes it a little bit more appealing, shows that there isn't any spectral broadening, looks really nice. The problem is though is that we can set that too high. In this example, it's set up to 550 hertz, saying don't display any Doppler shifts that are lower than 550. But at this point, we've gotten rid of all of our diastolic flow, and it's really changed the appearance of our waveform and making it look abnormal. So it's important, again, to set your wall filter appropriately so we're not getting extra junk in there, but not altering the appearance of the waveform. So to kind of summarize all this Doppler stuff that we've talked about, we have pulsed versus continuous wave Doppler. We have range resolution, which is a good thing. We can choose our sample volume. The problem is that it's got a limited max velocity, which is that Nyquist limit, and we're going to get aliasing with it. So goods and bads of pulse Doppler. On the other hand, with continuous wave Doppler, we have range ambiguity, and there's a region of overlap, so that causes issues and that we can't pick out where we are actually getting Doppler information from. But the good part of it is that we can get that unlimited max velocity and there's no aliasing. So remember the goods and the bads and the trade-offs of pulsed and continuous wave Doppler. Also recognize the differences between pulsed and continuous wave transducers. Again, pulsed Doppler transducers only need one crystal. There's going to be dampening material on it, which will result in a low Q factor, wide bandwidth, and lower sensitivity. And again, it's these three things that cause that aliasing. Continuous wave Doppler transducers must have two crystals, one to transmit, one to receive. These transducers are not going to have dampening material, which results in a high Q factor, low bandwidth, and higher sensitivity. And because of these, we have no aliasing. And some other tips regarding imaging versus Doppler. There's certain techniques that we want to use when we're trying to get that nice black and white picture versus techniques that we would want to use to get a nice Doppler picture. So when we are imaging items in the black and white mode, we typically want to try to get a 90-degree incidence on it. Whenever we have things that are perpendicular to our sound beam, the sound beam hits everything evenly and it looks really nice. So when we're doing real imaging, we try to go for that 90 degrees. Also, as we increase our frequency, we're going to improve our resolution, which just gives us nice, clearer, crisper borders. We have to use pulse wave, otherwise we would not get anatomical imaging, which requires a minimum of at least one crystal in our transducers. So these are kind of all imaging factors that we consider. The other side of that, though, is Doppler. The best that we can do is to come in at that 0 or 180-degree incidence. We want to be parallel to the sound beam that's coming in. We also want to use lower frequencies when we're Dopplering because that helps to avoid aliasing. Doppler can be out of pulsed or continuous wave modes. And then we need a minimum of 1 crystal for our pulse transducers or a minimum of 2 crystals for our continuous wave transducers. So the last bit of information that you guys need to know regarding spectral tracings and pulse wave and continuous wave Doppler is how all of the information coming back from those blood cells moving is analyzed and then displayed onto our machines. There's a lot more physics of all of this than we're going to get into. Again, it's going to be some more terminology that you'll need to know and pretty much the very basics of how it relates to Doppler analysis. So with spectral analysis, we know that not all the blood cells are traveling at the same speed or even in the same direction. What spectral analysis is going to do is going to break down all of those complex signals that are happening, that are coming back from all of those blood cells that are moving in different directions and speeds, and it's going to kind of break it down into building blocks. It's going to really simplify the signal. There are 2 methods that we use currently in our machines. The fast Fourier transform is what is used for the pulse wave and continuous wave spectral analysis, and then autocorrelation is used in color Doppler, which we'll talk about in the next video. There are obsolete methods because they are analog based. Again, remember we're in this digital world now with our machines, but you do still need to recognize that zero crossing detectors, chirp Z transform, and time interval histograms were all ways that we identified those blood cells and changed it into a spectral analysis. But again, these are all obsolete. We don't use these anymore. So fast Fourier transform and autocorrelation are current day use. So what is the fast Fourier transform? Again, terminology, vocabulary word that you need to know. You need to know that it's related to how pulse waves and continuous waves graph onto our machines. So the advantages of fast Fourier transform is that it is really very, very accurate. And what it's going to do is display all the individual velocity components that make up the complex reflected signal into something that we can kind of visualize and get diagnostic information from. The other thing the fast Fourier transform does is distinguishes between laminar and turbulent flow. When we have laminar flow depicted in our spectral window, we're going to have this nice kind of smooth line going throughout. We're going to have nice open windows and it'll be very smooth looking because all the blood cells are pretty much moving in the same direction at a certain speed. Turbulent flow, though, is going to look more chaotic and it's going to start to fill in our spectral window. It'll start to look more like this. You'll still get a nice waveform in there, but it's going to be kind of all over the place, really filling out that spectral window. And when we get that, we call that spectral broadening. Another way to think of the fast Fourier transform is that it almost takes the recipe that all those red blood cells are putting out there and then figures it out and gives us what we perceive to be our spectral tracing. So say this blood cell, this group of blood cells is sending back to the transducer this sort of waveform. And then this group of blood cells is sending back to the transducer something like this. And then this set of blood cells is sending back something like this. So the fast Fourier transform is going to take all these components of our recipe, add it together, and give us what we expect to see. So it's kind of a filter of sorts to give us a nice waveform in the end. So again, that fast Fourier transform, or FFT, looks at all of the individual frequency components that are coming back, does its spectral analysis on it, and makes a composite Doppler signal to which gets displayed onto our machine. So again, takes all of these little bits of the recipe, figures it out, and puts it into a nice spectral tracing. All right, so kind of a long lecture. I apologize, but there's just a lot of information that needed to get into this one. So big things from this lecture: pull out continuous wave versus pulse wave Doppler, what it means when you use either one of them, what the advantages and disadvantages of each are, and what the transducers look like and what components are in the transducers for each continuous wave and pulse wave Dopplering. You also need to know what aliasing is and how to correct it. We had those 5 methods of correcting it. I really encourage you to understand why the physics behind all of it work towards improving that aliasing piece of it. And then the last part that you'll need to know is what the fast Fourier transform does, how it helps our spectral tracing window, and what the outdated technologies are. So number 1, what are the advantages and disadvantages of continuous wave Doppler? Number 2, what are the key elements of a continuous wave transducer? Number 3, what are the advantages and disadvantages of pulse wave Doppler? Number 4, what are the key elements of a pulse wave transducer? Number 5, what is aliasing? Number 6, what are the 5 ways we can correct aliasing? Number 7, what are the outdated methods of analyzing Doppler returns and what is the current method used? And number 8, what questions do you have about this lecture?